Don't scare me. We are crossing the equator again. Well, again, for people who took PY105, you already saw that. 3 weeks behind, exactly 3 weeks ahead, so equator. And usually ship crews have some weird things to do. To newbies, we don't do anything. We just move on, hoping 3 weeks will pass quickly as the first 3 weeks passed. You can look up online lots of funny things. This is a summary of everything we've talked about last week. All right. I guess that's a sign. Let's see if that input is more stable. The Faraday's law, which has two forms, if we just use this ratio, that gives the average value of EMF induced in a closed loop. If a time interval is very, very small, we can get instantaneous, which is equal to the slope times -1 times the number of loops if we have several loops or turns. And mathematics tells us how to relate a graph and the slope. Just imagine a line, tangent, and if it angles like this, the slope is negative. If it angles like that, between 0 and 90, the slope is positive. We can just calculate rise over run. Yeah. And if we need to calculate electric current, we can just apply the old-fashioned Ohm's law, EMF divided by resistance. Yeah. Interesting. Some symbols missing. And I got two questions. That's the first one about a slope of a graph which is not shown here, but the flux. The flux. The flux is a number. We can always sketch a graph to see if anything happening to the flux. Maybe nothing. Maybe it's increasing. Maybe it's decreasing. Maybe it is changing back and forth. In this situation, we have to say something about the slope of this graph at t equals 3 seconds. And again, a slope is a number. As any real number, it can be 0, positive, or negative. So the choice is 1 or 2 or 3. And so write down just 1 if you choose positive, 2 if you choose negative, 3. And in 5 seconds, I'm going to switch to the next question. So just make your mind for this question. And the next question is about the same graph, but now it is requiring some calculations done. Now it is again about flux. And technically, if we use our TY105 experience, we can even plot, well, not plot, sketch the graph for the flux. But we don't have to do that. All we need is a number. If the flux changes from 0, what would be the final value of the flux? So this might require a little bit more time, so I'm just going to drink my coffee. So just for the second, a couple of people were late, so we had a question number 2 right here. For both questions, we have exactly the same set of equations on the screen, exactly the same graph for the EMF as a function of time. Little things which might throw you off. So in that case, you just have to ask a question or say some, make a statement, suggestion. And before moving on, I just want to take a quick look at the distribution for the question number 2. We do have some distribution, but we also have a winning answer. So one equation relates area, second equation relates slope. So since we are looking for the slope, natural choice of the equation is the equation number 2, right? And 3 seconds is here. We actually could calculate the value of this EMF with a straight line. But what's important is it is a positive value. So, well, here, okay. EMF at t equals 3 is equal to negative slope, which means slope should be equal to negative EMF at 3. And if this is a positive number, this is supposed to be a negative number. So the winning answer actually is wrong. Democracy doesn't work in physics. Logic works. So Does it mean the flux is positive or negative? Not necessarily. All we know is the slope. So the graph could have been like this, like this, like this, like this. And the next question kind of is related to what type of the graph should be happening here. So this is a value, an actual value of EMF induced somewhere. We don't know, but we don't care. Yeah? We know it's induced. And the graph says at t equals 3, the value is positive. That's it. And the slope should be opposite. So we use that equation just backwards. Now about the graph, well, technically, see, we have to start from this. And can we do it like this or like this? Again, same old trial and error method. So for this line, that should be the tangent line which indicates the slope. For this line, this should be the tangent line which indicates the slope. For those lines, the slope is positive. So none of those lines actually could work. Well, so we have to start from 0, and the slope should be negative. So technically we have two options, like this and like this, and only further analysis should tell us what should happen. But well, EMF is 0 at t equals 0. So technically slope should be 0. Zero slope means it should start horizontally, and then something starts happening to it. And well, it's a fictional problem. Now what should happen? Well, the actual value of EMF remains positive all the way up to 10, which means the slope of the flux should remain negative all the way up to 10. But here we should have something change. So probably the curvature changes, something like this. Again, if we remember a relationship between the position graph and velocity graph for motion with constant acceleration, this is a very similar situation. That looks like a position graph, and that looks like a velocity. So if velocity is a straight line, the position graph should be a parabola, something like this. Well, anyway, what we're looking for is the final value, and actually it has to be a negative number. So you should have been choosing probably 0. Or if you assume magnitude, so this is the final value of the flux. So now, of course, we just have to apply the equation which relates the area and two numbers, initial and final. That's supposed to be 0. That's supposed to be an unknown, which we're looking for. That's supposed to be equal to this area, which is two triangles, but we can actually flip them, and that will make one rectangle. 10 seconds by 10 volts. So 10 times 10, 100. So negative a question mark equals 100. So that's supposed to be negative 100. And a negative slope, negative flux means that for this particular situation, magnetic field and area vector are opposite to each other. Why? We don't know. Someone made that area vector point in that particular direction. But if the question would have been, is magnetic field parallel or opposite to area vector, we would have to say opposite. So here, all questions technically, all answers technically wrong. So you could have chosen 0 usually for that situation, or 9. I don't remember what's inside. What does it say? Any questions? Did you have a question? Okay, moving on. So this is an illustration of a relationship, technically geometrical or algebraical relationship between slope, a function, and the slope of that function. And this is why we study all this stuff. The practical reason. Generators. Yeah. We need a lot of electrical power. We consume it every year more and more and more and more. And first of all, we remember that if we have a battery and connect it to, well, if you look through, there is a motor connected to a motor. It starts doing some work. But now we want to do it backwards. We want to use magnetic field acting on, well, a coil to generate that electricity. So we are very lucky. Nature has symmetries. We just have to inverse the process. Instead of consuming electrical power, converting into mechanical energy, we can spend some mechanical energy and transfer into electric energy. Sometimes it's easier to do, sometimes it's harder to do. You can actually power up an actual bulb from where? Home Depot, from Home Depot. So you just have to spin it fast. And of course, they all have at least two exactly the same elements, a source of magnetic field and a spinning coil. When we start spinning a coil, we induce EMF, which can be consumed, again, to demonstrate that this is really a completely symmetrical situation. It doesn't really matter which we use as a generator, as a motor. So we can use this as a generator. That becomes a motor. We can use this as a generator. That becomes a motor. And the only difference is which type of energy we transfer into which type of energy, but what's inside is the same. Source of magnetic field and spinning coil. And if we want to calculate the EMF induced, well, we got to do this. First of all, in this situation, magnetic field remains constant. The area of the loop remains constant, but what we change is the angle. And normally, of course, the angular speed is constant. And if the angle changes in time linearly, that makes flux change in time as a cosine or sine. And this is an equation which has been studied before extensively in the topic which had a name, simple harmonic motion or oscillations. So everything we've learned about simple harmonic motion now can be directly applied to generators, including this equation at the bottom. If flux changes in time, EMF changes in time, of course, but the flux has its maximum value when magnetic field is parallel to area vector perpendicular to the loop. Then flux changes to 0 again to maximum, to 0, to maximum. So EMF also should oscillate 0, maximum, 0, maximum. And the maximum value is equal to the number of turns, if we have several, times maximum flux times angular speed. How do I know? Well, I use the theory from simple harmonic motion. And in mathematics, nothing depends on letters we use. So we can replace x with a flux, v with a negative EMF. There's only one difference, that minus. And everything we've learned about simple harmonic motion remains true. For example, this is just a copy from a slide. If position changes in time like cosine, velocity will be sine. That will be the maximum value of velocity. And here we just replace letters, and we get maximum peak value of EMF will be equal to, well, we just adding one more parameter, number of turns. Yeah. And again, everything from this slide can be applied to the generators, everything. Yeah. And that's what we have to do. So first we have to sketch the graph for the flux. How does it change? Well, in general, we have two simple situations when the function is pure sine or pure cosine or anything in between, and physically it doesn't really matter. So since I see a cosine, I can start from a cosine. This is one whole period for the flux, and it keeps changing. So whole period, yeah. It means during this time, the coil makes one whole revolution. This is a half of a period, a quarter of a period. Now, first thing to do is to sketch a graph representing the behavior of the slope. Well, first, no slope. The flux starts horizontally, and then the slope is negative. The slope is negative, so it goes into the region of negative numbers. Of course, we're just doing the same kind of work we did before for velocity and position, so nothing different. A quarter of a period, a half of a period, 3/4, and this. So we should reach maximum, then we should go back to 0, another maximum, back to 0. So something like this. But that's the slope. People sometimes forget we have to do one more step, because EMF is, well, technically some negative number times slope. So all we have to do is just flip the graph. So it will be something like this for one period. And of course, if we really want to, we can add a graph for electric current, which is basically a copy of a graph for the slope times -1 for the EMF. That's it. And we can repeat the same procedure for any graph. There will be a similar set for sine. So as you remember, mathematically, there is no difference between using a sine function or a cosine function. We always can convert sine into cosine, cosine into sine. So technically, it doesn't matter. All we have to do is just watch closely what's happening to the slope and flip the graph for the slope. Question for the graph on the left. Can you choose a time when EMF reaches its second maximum? Now we should go back to a discussion about terminology. If you look at this graph, and any graph technically is infinitely long. We just look at one period. Technically, we don't even need a period. We need a quarter of a period to figure out all information. But in general, the graph, of course, goes infinitely in both directions. So for this graph, this time people would call a time when flux reaches first maximum. Even mathematically, that's a minimum. Because when people say first maximum or first minimum, they mean the magnitude. They don't say it every time. But they mean the magnitude. And this is, well, if we start from 0, when the flux reaches second maximum, which is physical maximum and mathematical maximum. This is if we start from 0. When the flux reaches the third maximum, which mathematically is a minimum, and physically is a maximum of the magnitude of the flux, etc., etc. But the question is not about flux. The question is about EMF, so you have to make a sketch for the EMF as a function of time. And point your finger at the first maximum, then at the second, then read the time, and that's it. And we can use the analogy from the past in simple harmonic motion. We know that, for example, when a cart has been released from rest, it oscillates back and forth, and when it reaches maximum position, velocity becomes 0. When it travels through equilibrium, x is 0, velocity reaches maximum. So those two maxima alternate. And exactly same behavior we should observe here. This point represents 0 slope, so EMF should start from 0. And of course, that graph represents negative cosine, so this is how we can write it down. By the way, this graph also tells us how to calculate the period, and if we know the period, we can calculate that omega thing. So, period. That information goes from the picture. Can you tell me? The period for this graph, from here to here, what time passes? From 0 to this. From here, you see? From here to here. That's a period. That's t equals 0. 8, yeah. So a quarter, a half, 3/4. So that's supposed to be 2, 4, 6, 8, 8. Omega will be 2 pi over t, or pi over 4 radians per second, if we need it. Now, and during the first quarter of a period, the slope is positive, which means EMF has to be negative. So we should go into negative numbers. That's it. That's all we need to know. Now we just it should reach the first maximum, which is mathematical minimum, when flux reaches 0 first time. Then it should go to 0 when the flux reaches maximum. When the flux is 0, that's where the second maximum is reached. T of second maximum equals 6. And then, by the end of the period, flux reaches maximum, but EMF reaches 0. And this is actually negative sign, yeah, negative sign. Well, it was basically a review, yeah. Simple harmonic motion, exactly same equations, exactly same mathematics, just different letters. Flux is acting like position, x, and the EMF is acting like minus v, -1 times velocity. This is a practical problem, yeah. This type of a generator, hand crank generator, yeah. So we just read number of turns, n 50. Each loop has certain area, 3 centimeters by 3 centimeters, 0.03 by 0.03. So the area will be 0.03 times 0.03, which is 9 times 10 to the -4 meters squared. So spins at 500 RPM. What does RPM mean? That's it. So we need to convert it into radians per second. So 500 a minute per minute, 60 seconds, and 1 revolution is 2 pi radians. So 2 pi. Now, a uniform magnetic field with a given strength, 2 Tesla. Initial orientation is such that initial current as its negative maximum. Okay. So if I wanted to make a sketch for the graph for the current as a function of time, it should start from this. And then electric current should go to 0, to second maximum, to 0, etc., etc. That's supposed to be 1 period. 1 period, which is actually supposed to be equal to 2 pi over omega, wherever it is. And that, so, now for the flux, actually, that's exactly the same, no, different. All right. So, first of all, if the current is at its maximum, that means EMF at its maximum, which means flux should start from 0, they alternate. If the flux starts from 0, next value should be positive or negative. So if the slope for I is positive, which means we don't care about slope for I, actually. The actual value of current, let's say here, I is negative. Actual value means EMF is negative. Hence, slope for the flux should be opposite of that, positive. So it should have positive slope. That's it. So it should go like this. All we need to know is to see how it begins, because we know the rest is just, again, sine or cosine. I always like to see 4 quarters. And if it would be Py105, I would ask you a question. How many quarters in 1 period? You would say 4. I would say yes. That's why we call them quarters. Maximum, 0. Weird maximum, which mathematically minimum, but for us is maximum. So that's how the flux would look like. Normally, we don't really care about the actual function for the flux. Normally, we just care about maximum value. That's it. Now, we want to write an equation in general. And EMF supposed, well, actually, since we do in EMF, don't do in current, so just to practice, EMF should look exactly like current does. And now we can write an equation. It is a negative cosine too soon. Just E max times cosine omega t. Omega t. And that's it. We know omega, how to calculate maximum. So number of turns, and for each turn it should be equal to maximum flux times omega. And for the maximum flux, we always get area times B, A times B. I'm gonna do that calculation. You can finish. I can finish it later. That's it. Very straightforward from my point of view. And if you want to, yes. If you want to look at the orientation, well, that's supposed to be the initial orientation. If the flux is 0, so magnetic field lines shouldn't go through the loop at all initially, and then it starts turning. How should it turn from this? If that picture represents time equals 0 in a fraction of a second, in which direction should it move? Counterclockwise or clockwise? Well, in a fraction of a second, flux should become positive. So we can imagine if it turns this way, the angle above 90 gives a negative number. So it should start spinning in this direction to make flux positive, but then it keeps spinning in the same direction, the flux changes. And that induces EMF. Yes? I just said trial and check. You only have two options to choose from. One option has a name counterclockwise, second option has a name clockwise. So for this option, flux would become negative. That is wrong because the graph says the flux is supposed to be positive. So yes, I don't understand. What do you mean? Electric current also constantly changes. This is the graph on the left for the electric current. How do I know? Because we told that electric current at t equals 0 should be negative and should be at the maximum. That's it. You see? Negative maximum at t equals 0. That's I don't understand. I know that current is negative. I know initially this coil will spin, what did you say, clockwise? Yes. That's not the current, that's the area vector. Oh. Because the rule is, if we know, if we're told to what is the direction of a current, we use the right-hand rule to relate current and area vector. If not, we just pick a direction for the area vector. So that's the reason I wanted to point out. So you can apply, okay, that's what probably That's what might help, probably. If we imagine we look straight above. So right now, right here, this picture has, this picture, which we called before, has no magnetic fields traveling through the loop at all. But when it turns a little bit, I don't know how to draw it, let's say like this. And so it should have some magnetic field. So in this situation, well, first of all, if it turns, area vector also turns. So you see, you have to be spinning. You have to be attached to the coil and spin with it to look at the same area vector. But before, after to oppose, so if it increases, it should oppose, it should point in to the screen, and the induced electric current for that second supposed to be like this, which we call counterclockwise, but that's a different counterclockwise direction, not that direction, because that direction is from your perspective when you look at the screen. And this counterclockwise direction is from perspective of a different person looking straight at the area vector. And see, you're forced to say me all this stuff, which is not easy for me. So, and from that perspective, that's supposed to be this. And that will happen for a quarter of a period. Then the electric current changes its direction. But we don't change the direction of area vector. If we set it to this direction, we keep it. Relative to this direction, current now in a quarter of a period becomes clockwise, and then counterclockwise again, and then clockwise, but relative to this fixed direction. So we have to imagine that we actually kind of sitting right here and spinning with the loop. So for us, area vector is always the same. So this is the next fraction of a second area vector like this. Magnetic. Oh, sorry. I think that I know what you wanted to say. I said clockwise. So, yeah. Come on. Into the screen, clockwise, into opposite to, so this direction, opposite to area vector, this direction. Thanks. Yeah. So this is everything together. Pictorial method, Lenz's rule, EMF, Faraday's law, but it requires kind of practicing in switching point of view in your mind from different perspective to another, and back and forth and back and forth. Anyway, once in the past we've used this name, RMC, root mean square. Now we can give an official definition. That's why we call it root mean square, because it's just maximum divided by square root of 2. That's it. So it's not a very important value for us, just a name. And again, this graph shows that changing flux and changing current reach maximum at different time. The maximum between flux and the maximum between current shifted by a quarter of a period. Okay, another practical application of this theory, transformers. A transformer transforms. That's not the transformer which you can see in a movie currently. Although I kind of like Mark Wahlberg, so probably I will see it eventually. I'm gonna need one more power outlet. So we need two coils like this setup. Here I have a coil which has 800 turns and another one which has 200 turns. How do I know? I can read. Very helpful skill. And all we need is a generator. Here I have a function generator, and now I can measure the voltage across this coil, and I can measure the voltage across this coil. We can see this is close to 4. Now, this coil has 4 times more turns than this one. Of course, they have resistance, and of course, an ideal transformer doesn't exist. Ideally, we would read 16, 4 times 4, 16, but we read slightly lower number. But we will read even lower number if we disconnect the core. In that case, it does practically nothing. Why? Well, we need magnetic field travel through both coils as much as possible, so that's why the transformer needs a complete core. The magnetic field lines here inside of this iron core, and one coil now is acting like a source of magnetic field, but that magnetic field generates EMF into the second coil, and we call them primary and secondary. Which is primary? Well, right now, this, because it's connected to a generator, but of course we can just switch them, and this will become primary, this will become secondary. But now the voltage should go from high to low, to be about a quarter of that. About 1, less than 1. So, see, and of course, the theory is very clear. It's based on the straightforward application of the Faraday's law. Assuming there is no loss of energy, there is no loss of any magnetic field, the EMF induced in a single loop in both coils supposed to be the same. But for the first coil, it should be equal to the voltage divided by the number of turns in the first coil. For the second coil, it should be equal to the voltage divided by the number of turns in the second coil. So we have the first relationship, which relates the voltage and number of turns. Second relationship is basically a law of conservation of energy. Assuming there is no energy loss, the energy we pump every second into the first coil should be transferred to the second coil. And the energy, on average, technically those supposed to be RMS, root mean squares values, or maximum values, not instantaneous. But we get a second equation which relates electric current in two coils. And when voltage goes up, we call it step up transformer. But when voltage goes up, electric current goes down. When voltage goes down, we call it step down transformer. But when voltage goes down, current goes up. And we can use this to manipulate with electric current and voltage. This is how we use it. The power plant generates very, very high voltage, mega volts. And then we use transformers as a series of transformers gradually. First, we actually jump it to even higher voltage to decrease current, to minimize the loss to thermal, to heat. But then gradually we go back through a set of step-down transformers to eventually 120 volts. RMC. And unfortunately, a lot of energy getting lost to heat, because even if the current is small, wires are very long. So if you remember, Q equals I squared times resistance. So ideally, it would have been nice to have wires with no resistance. And in 1986, high temperature superconductors were found. But unfortunately, those materials are ceramics. You can't make a wire from ceramics. So far, we still use mostly copper wires. And a question. This is what is going to happen. I've got a multimeter, and I've got two coils. And I will make one coil to be primary, second to be secondary. Secondary is going to be this one, of course, because we want to measure. We want to measure electric current, EMF induced, and this will be my primary coil. I just need to connect it to a battery. Come on. So I'm just giving you time to answer the question, right? I really need a switch. I can just take this wire and touch it. They're supposed to be close to each other. All right, pick your answer. Well, you can watch right here. You can watch here. Close. Did you see anything? Watch closely. Did it move? Did it move? Hard to tell, yeah? So what do we do? We just saw we need a core. Now this magnetic field will travel almost without any loss through the second one. That's what's happening. This is a transformer. I can do something like this. AC. And, so we just saw what's happening. I'm connecting the battery to the primary coil, and I keep it connected. So the current wasn't zero, but only for a short period of time. So it jerked and come back. Do I have electric current traveling through this coil? Yes, I do. It's a closed circuit battery coil. Why I don't see anything happening in this anymore? Faraday's law. To observe EMF induced, we need changing flux. And magnetic flux here is not zero, but it is constant right now. It only changed when I was touching or removing the battery. And if we want to plot a graph which helps us to see what was happening to electric current, we just have to start from sketching a graph for the flux. The flux, well, first of all, as we know, it's B times A times cosine theta, and we also know that B is proportional to electric current in a solenoid. So we close the switch and the current starts from 0, goes to some maximum value, and so does the flux, and it reaches certain value, and after that it remains constant. So this is where flux was changing. And electric current, well, I just want a magnitude. I don't care about plus and minus. Electric current also should have a peak somewhere in between 0 and maximum. But then here the flux stops changing, remains constant. The flux remains constant. The change becomes 0. No induced EMF, no induced current. Exactly what we saw. Just again, practicing and applying. Faraday's law. No change, no EMF, no current. Any questions, please? Well, so we see it, and now the Lenz's law also has certain practical applications. And before we go to those applications, let's just take a look at a couple of interesting experiments which help to understand why the minus. I have two loops here. The one on the left for you is continuous, and this one has a cut in it. See? Oops. And I have a magnet. So if I'm doing something like this, nothing is happening. But if I'm doing something like this, we can see the influence, the magnet influences this, and we know why. It's a closed loop. The changing magnetic field induces EMF here and there. But in this loop, EMF actually makes electrons travel, so there is electric current. Here, electrons can't jump across the opening, so there is no electric current. Electric current here induces magnetic field. This loop starts acting like a magnet. Two magnets either repel or attract each other. This is what we call repulsion. What does it mean? It means this coil starts acting like a magnet with the same pole facing the magnet. That's repulsion means. So if this is my, let's say, north pole, that means here, north. So magnetic current is supposed to be this way to make north pole facing this north pole, and they repel each other. But I can do it differently. I can place it in first, and now move it out. And that's what we call attraction. So now, at the moment when north pole was facing this loop, the current was generating magnetic field in such a way, so it would have south pole close to the north pole, so they would attract each other. So, see, that's what we usually call opposite. And experiments like that tells us how to relate actual value of induced EMF and flux. And I need here. This is aluminum. So if I drop a chalk and quick enough, and I have to be quick enough to catch it because it falls down due to gravity. But I don't have to be quick enough if I drop a magnet, because it takes almost forever. Why? Because when the magnet starts moving through this tube, it starts inducing electric current. But that electric current generates its own magnetic field, which slows it down. And actually, it's very easy to understand from energy point. It can't speed it up. In that case, we would get the infinite amount of energy. We just get a tube, a magnet, put it in, and it's, travels faster and faster. So it has to slow it down. But this is a slightly different situation because we're generating electric currents in a bulk amount of material. Those type of the currents have a name, eddy currents. And they heavily used in brakes. Oops. Here I have two pendula, aluminum again. So from the point of view of force of gravity, there is no difference at all, practically. But now I can place them in magnetic field. And what do we see? One practically is not affected, second stops very quickly. Because here, because of these cuts, we cannot induce strong electric current. Electrons cannot jump across. But here we can easily induce a relatively strong electric current. That electric current induces magnetic field, which starts interacting with this one, and it stops. And locomotives, for example, have brakes based on this effect, because it's easy to, nowadays, it's easy to make a very strong electromagnet. And the wheel is made of some conductive material. If you want to stop, we just turn on the electromagnet and do it to interaction. They don't touch each other. Yeah? They don't have to, which is good. There's no friction. The locomotive stops. Wrong. Here. Well, so we did see that. We did it, and so the loop starts acting like a magnet, and repulsion. Yes, so that was the question about. It wasn't a Weber-Sein question, just a question. And eddy currents help to stop fast-moving, heavy machinery. Now the last thing to look inside of all materials, the last thing left is to look inside. If we have a magnet or iron or any material which strongly interacts with magnet, we call it a ferromagnetic, iron. Well, this is an ideal situation, never happens, but ideally, that's what we would see if we could look inside of an ideal magnet. And the reason for that, well, each arrow represents just a tiny, tiny magnet. The reason for that, electrons. So first of all, electrons move, so they generate electric current, and electric current generates magnetic field, but also electrons have a spin. That's a quantum mechanical entity, the analogy is like electron spins about its own axis, which is just analogy. It also acts like a magnet. So in ferromagnetics, they align in, well, let's say mostly the same direction, so the strong magnetic field can be generated. But we can destroy it by very simple means. Oops. We've got so much expensive material here. I was afraid I have lost it. Not easy to find. Well, the magnet acts on spins inside the iron nail, and they become, well, pointing mostly in the same direction. And where's the magnet? Here, the magnet. So they start to attract each other, and oops. If it's in equilibrium, that means force of gravity and magnetic force are equal to each other. But I can destroy the order. We know that if we heat it up, molecules start moving faster and faster and faster and faster and faster and faster. When it reaches a certain temperature, it loses its magnetic properties. That temperature has a name, Curie temperature. And for iron, it's not too high, so we can use a standard equipment to reach the Curie temperature for iron. Of course, if we go backwards in temperature, we should expect more and more like a strength in magnetic properties, and we will. But first, let's take a look at a couple of more things. This is some kind of a crystal. Chemicals are for laboratory and educational use only, so don't eat. I'm not gonna. I just need to make it stand. Now, I got a magnet, and I see that the magnet affects it. How? How? Attracts, but that's not a very strong attraction. You see, I need a strong magnet. I can't pick it up. This is what we call a paramagnetic, and the difference between ferromagnetics, paramagnetics, and ferromagnetics, spins responsible for magnetic properties. In paramagnetics, those spinning electrons. But interestingly enough, we also have materials which don't like magnetic field, like a graphite. This is like a huge pencil, piece of graphite. Well, actually, I don't need it anymore. What's going to happen now? It should have leveled. I don't touch it, but it moves away. A fabric like that has a name, a diamagnetic. And turns out that a superconductor is an ideal diamagnetic. It just hates magnetic field. So when magnetic field starts getting in, it wants to get rid of it. And to do that, it can excite electric current, which can travel inside of a superconductor forever. Well, all we need is a very low temperature. But this is a high temperature superconductor. For the high temperature superconductor, low temperature actually, well, I forgot to switch that camera. So until 1010, Echo 360 was capturing this. Well, things happen. So, camera. Let's see. Okay, autofocus seems working. All I need is liquid nitrogen. Which I used twice today for this demonstration and for another demonstration. Well, first I need to pour it from a big dewar into a smaller container. Stop boiling. Eventually should stop boiling. You can't put it in it. It doesn't want to be there. But if I try a smaller one, floats. Can even spin it, it spins. Yeah, I'll try. It's not. Okay, you can see how it spins. Let's try this one again. Oops. Come on. Those magnets. Come on. Spin. Doesn't want. Too heavy. Yeah. But small one, see, wobbles. And that's what it does. And it's going to spin, well, of course not forever, but until the liquid nitrogen keeps it colder than the transition temperature, when this ceramical piece becomes superconductive. And since I'm using liquid nitrogen, there's one more interesting demonstration, which I really like. The last for today, I guess. That's called, this device has a name, jumping ring. It also has two rings. One ring has a cut in it. Come on. This one. So you would know this is continuous. And of course, if this is basically now a transformer, primary coil, secondary coil, but nothing going to happen with this one. Electric field at the location of the coil is not zero, it's being induced. But we cannot induce electric current, and if there is no current, there is no induced field which would interact with this one. But this one, that's why we call it jumping ring. This one, again, clearly shows the repulsion. So as long as I start inducing magnetic field inside this core, that core induces EMF in this loop. EMF induces electric current. That electric current induces magnetic field, which is opposite, and it jumps. And now I want to cool it down. Still, yeah. Still floating. Now I'm cooling it down. Where is it? What do you think should happen now if I do exactly the same experiment? By cooling it down, what do I change? Oops. I change the resistance. Remember we talked about, for example, the filament in the bulb. When we heat it up, resistance increases. So if I cool it down, resistance decreases in both experiments. This ceramic piece now has zero resistance. We could actually try to measure and would have been zero. And same happening with aluminum. When we cool it down, the resistance decreases, less motion. And when the resistance decreases, that's a coincidence. Happy coincidence, first time in my life. But from now on, that's exactly how I'm going to do it. So when the resistance decreases, of course, same EMF induces higher current, stronger magnetic field induced in it. So the repulsion is stronger. And don't touch it until it warms up to room temperature. You can get burned. Well, so just want to untangle everything. Put it down, put it away. Now, we have seen everything. Which means it's time to start a new topic. The last topic for this week, sound. Well, sound is a wave. So first we have to talk about waves in general. So there are some helpful links, and we will be using those applications just for the examples here. A wave. This is an official definition of a wave. A wave, it's a disturbance which travels away from a source. And the first helpful link would lead to this particular applet. So, how do I make a wave? That's it. This wrench is a source. Well, technically my hand is a source. My mechanical energy is being transmitted, moved away from my hand through, well, if it's a rope, so through a rope or something else. In this particular situation, that is a rope. So I am acting on a piece of rope which is in my hand. That piece of rope, due to tension, is acting on a piece of rope next to it, on the next to it, on the next to it. That's how a wave propagates. And we can see, all we need to understand how one pulse propagates. In that case, every wave is just a set of pulses traveling away. In real life, of course, there is some friction. We can play with no friction. In that case, the amplitude of each pulse is the same, doesn't change. Increase the friction, of course, some energy getting lost. Initial amplitude is large, but then eventually it goes to zero. We can play and see how, for example, force of tension affects. It travels now much slower. No matter how hard I try to move it, it travels slow. But if I change the tension, increase the tension, it makes the wave travel faster. And there are two types of waves: mechanical waves, like in a rope or on the surface of water, and electromagnetic waves, and also gravitational waves, as we know now for sure. Difference is that mechanical waves need some medium, a rope, air, water. They can't travel in vacuum. Electromagnetic waves, which is just electric and magnetic field coupling with each other, traveling in space, they don't need any medium. They can travel on its own. We're going to talk about it in a week. By a shape, waves divided in two groups. If you look at this picture, at this applet again, we observe two types of motion. We can look at a single point, and that point travels up and down, up and down, up and down in this applet. So a wave doesn't move matter. It doesn't move in space away from the source. Only energy is being moved from the energy source to all parts of the space. This motion, of course, takes certain time and distance. So this motion, we call it wave motion. So wave travels horizontally, and we can calculate how fast. We would call it speed of wave, or speed velocity, wave velocity. But if we look at individual particle, wave particle, it travels up and down, up and down. What kind of a motion is this? How do we call it? Oscillations. So again, a wave is a continuous combination of simple harmonic motion. Well, simple harmonic wave. Of course, the wave might be more complicated, but the simplest situation represents just a combination of many, many, many simple oscillations. They all, well, neglecting friction, they all happen with the same amplitude, same frequency, same period. And we know for the oscillation, velocity changes maximum when the particle travels through equilibrium, slows to zero, reaches maximum, zero, and again. So the maximum speed of this particle has a name, maximum speed of the wave particle. That's it. So we have two different speeds, two. And we can see in this example the propagation happening to the right, but each individual particle moves up and down these two directions, right and up and down, perpendicular to each other. When that happens, wave has a name, the transverse wave. That's not always the case. Sound waves, for example, are different. In a sound propagates from the source, and, well, particles, molecules, move in the same direction, not up and down, like left, right, left, right. Waves like that have a name, longitudinal. And this is the last question before we finish the class today. So I'm going to give you 1 minute. It's supposed to be a question when everybody answers absolutely correctly, because there is no reason for not doing that. The applet had shown a model of a transverse waves, and now all we need to do is just take a look at the model of a longitudinal wave. You can make it at home if you have just a slinky, and be patient. Now I will reveal it to you. So a simple single pulse travels horizontally. But if I start making many pulses, that's going to be a wave traveling also horizontally. So these turns, windings, they don't move away from the source. They move about equilibrium position. For each, there's its own equilibrium, and they move left and right about the equilibrium. But the propagation is happening horizontally also. So this is a model of a longitudinal wave. Survey says, what did you say? Of course. All we had to do is just to apply a definition. Thank you very much. We are done. Yep. If you answer 2 or 3, ask yourself why. And today we have a lab which set is in 1:30.
Next Monday, Tuesday, after the English lab, that same Monday.
No.
On the schedule, it says on the 1st and 2nd of August that there's lab.
I'm going to check. I doubt that.